The section you're about to embark on is all about redox reactions. Redox reactions are reactions that involve the transfer of electrons from one reactant to another. Each element has an ability to attract electrons. The strength of this attraction can be measured using a scale of electronegativities. We're going to learn more about this later on in the year, so this is just a brief explanation. Remember, on the periodic table, the metals on the left-hand side of the table prefer to lose electrons, whereas the non-metals on the right-hand side of the table prefer to gain electrons. You might want to remember it as on the left-hand side the metals lose electrons, whereas on the right-hand side the non-metals gain electrons. So that can be quite a nice memory trigger. LG, like the brand name, or Life's Good, or something like that. This all becomes particularly important when we look at how atoms covalently bond within molecules or perhaps within compound ions. Let's look at hydrogen chloride, for example. Hydrogen in group 1 has got 1 valence electron. Chlorine in group 7 has got 7 valence electrons. They bond covalently, they are going to share their electrons. So let's orientate those. Because chlorine has got a higher electronegativity, it's going to have a greater pull on that electron pair. Remember, these pairs, these are called the lone pairs around the edge, and the pair in the middle is called the bonding pair between the hydrogen and the chlorine. Now, because hydrogen has got a lower electronegativity than chlorine does, hydrogen is going to have less of a pull than chlorine does. So what's going to happen is that those electrons are actually going to spend more time in chlorine's orbitals than they are in hydrogen's orbitals. Oxidation numbers are basically a measure of the pull that each of the elements in a compound have on the electrons. More specifically, it's the definition in your textbook on page 77. The oxidation number of an atom in a compound is the charge it would have if the electrons in each of its bonds belong to the more electronegative element. For example, in HCl that we looked at before, the shared electron pair would be considered to belong to the more electronegative chlorine. Oxidation numbers have both a sign and a number. The sign is a reflection of its ability to attract electrons. If it's good at attracting the negative electrons, it would have a negative sign. If it's not as good, it would have a positive sign. The number is related to the number of electrons that are involved. There are a couple of rules for assigning and using oxidation numbers, and we're going to go through them now. Rule number 1, the oxidation number of any uncombined element is 0. So that means it's an atom on its own, it hasn't bonded to anything else. That could be something, for example, like sulfur or perhaps iron, any element that can exist on its own. Don't forget about the elements that like to exist as pairs, so the diatomic molecules, they are also going to have an oxidation number of 0. That would be things like your halogens, like chlorine, for example, would exist as Cl2, or hydrogen, oxygen, and nitrogen. Remember, any of the gens are diatomic molecules: hydrogen, oxygen, nitrogen, and the halogens. Okay, rule number 2. The oxidation number of an ion of an element is the same as its charge. So if we look at some examples, the oxidation number, which we denote as On, of sodium, we look at the charge of the ion, which in this case is a positive, but there's a 1 in there as well that we need to remember. So the oxidation number of sodium ion would be +1. Don't forget to write that 1 in, it is important. If you look at the next one, the sulfide ion has got a charge of 2-, which means that that oxidation number would be -2. Last example, the aluminium ion has got a charge of 3+, which means the oxidation number would be +3. The third rule says that the sum of all oxidation numbers in a compound is 0. That means the oxidation numbers of all the different atoms that are making up a compound must add up to a total of 0. So for example, in something like sodium chloride, the overall oxidation number is 0, or in hydrogen sulfide, overall oxidation number is 0, which means all of those oxidation numbers of the individual atoms add up to that. This next rule refers to compound ions, which are those polyatomic ions that you learnt about in Form 3 and we've continued to use in Form 4. And basically it says that the sum of the oxidation numbers in a compound ion is equal to the charge on that ion. So it's very similar to rule number 2. So for the oxidation number of a sulfate ion, because it's got a charge of 2-, it's going to have the sum of the oxidation numbers in the sulfate ion is going to be minus 2. The sum of the oxidation numbers in the ammonium ion, because that's got a charge of positive 1, the sum of the oxidation numbers is going to be plus 1. Because the halogens are in group 7 and have a charge of minus 1, we would expect their oxidation number to be minus 1, as rule number 5 mentions, but it's got an extra little bit about it. It says that the oxidation number of the halogens is minus 1 when the compound consists of 2 elements only. So, for example, if you've got looking at sodium chloride, where there's only sodium and there's only chlorine, then the chloride is going to have an oxidation number of minus 1. If we look at magnesium bromide, again, only 2 elements, magnesium and bromine. So bromide's going to have an oxidation number of minus 1 there. If you look at something like sodium chlorate, that's going to have sodium, chlorine, and oxygen as elements, which means that the oxidation number of the chlorine in this instance is not going to be minus 1. So the rule doesn't apply to something like that. I'm going to show you how you would work out the oxidation number of chlorine in sodium chlorate a little bit later on. Okay, number 6, the oxidation number of oxygen in a compound is nearly always minus 2. Certainly for the kinds of compounds that you're going to encounter, it's going to be minus 2. So for example, if we've got sulfur trioxide, the oxidation number of the oxygen here is going to be minus 2. The fact that there are 3 of them is something that we'll need to take into account, and we'll do a couple of examples with that later on. With carbon dioxide, for example, again, the oxidation number of oxygen in this compound is minus 2. Our last rule says that the oxidation number of hydrogen in a compound is nearly always plus 1. Again, for the kinds of compounds you're going to encounter, this is going to be true. 2 examples, if we look at water, in water we've got hydrogen and we've got oxygen. In this case, the hydrogen has got an oxidation number of plus 1. Similarly, for hydrogen chloride, the hydrogen has got an oxidation number of plus 1. Now I just want to draw your attention to this. Going back to rule number 3, we said that the oxidation number of an entire compound is going to be equal to 0. So the oxidation number of water would be equal to 0 because it's a neutral compound. This makes some sense. If we go back to our previous rule, rule number 6 said that the oxidation number of oxygen is going to be minus 2 in this case, and the oxidation number of hydrogen we now know is going to be plus 1. But we know that there are 2 of them. We mustn't forget that. So we need to multiply this plus 1 oxidation number by 2. If we take those 2 oxidation numbers into account, 2 times plus 1 is going to be plus 2. Add that to minus 2. That's going to get us a total of 0, which tallies with what we know from rule number 3. You might be asking yourself what the point of all this is. In this case, rule 6 and rule 7 just serve to confirm each other. But where this becomes really useful is when you've got elements that have a variety of possible oxidation numbers and you are trying to find out exactly which oxidation number it does have. So that could be for something that has 2 or more atoms in a compound, and you use the rules 1 to 7 that you've just learned in order to figure out the oxidation number of the unknown atom. Okay, let's try an example. This one asks what the oxidation number of sulfur is in sulfuric acid. Now remember, sulfuric acid has got this formula, H2SO4. So sulfur is not one of the elements that came up in any of our rules before, which means that sulfur will have a different oxidation number depending on what compound it's bonded in. So to find out what its oxidation number is in sulfuric acid, we're going to apply our other rules. Now we know a few things. Firstly, we know that hydrogen always has an oxidation number of positive 1. We also know that oxygen always has an oxidation number of minus 2. But we do need to take into account the fact that there are 2 hydrogens and 4 oxygens in this compound. So we're going to multiply our positive 1 oxidation number for hydrogen by 2, and we're going to multiply our minus 2 oxidation number for oxygen by 4. We also know that the overall sum of the oxidation numbers of sulfuric acid needs to add up to 0. That was coming from rule number 3, because this is a neutral compound. So what we need to do is we need to add together the positive 2 contribution from hydrogen together with the oxidation number of sulfur, which we're going to find out now, together with the -8 overall contribution from oxygen, and that total needs to come to 0. So we can work this out. We've got the +2 from hydrogen, we've got the -8 from oxygen. That means that there needs to be a contribution of +6 from sulfur in order for the total to be 0, which means that the oxidation number of sulfur in sulfuric acid specifically is +6. Similarly, in this example, they're asking what the oxidation number of sulfur is in sulfurous acid. Now, sulfurous acid has got a formula of H2SO3, not H2SO4. So let's do our calculation. We're going to have 2 hydrogens, which have got an oxidation number of +1, and we're going to have 3 this time, 3 oxygens, each with the oxidation number of -2. Again, overall compound is 0, which means the oxidation numbers need to add up to 0. If we work this out now to work out what the oxidation number of sulfur is, we're going to see that in this instance we've got the +2, we've got the -6, which means this needs to have an oxidation number of +4 in this compound. So sulfur in sulfurous acid has got a oxidation number of +4, whereas in sulfuric acid it's got an oxidation number of +6. So as you can see, sulfur, same element, but different oxidation numbers because it's bonded in different compounds. Let's look at another slightly different example, the oxidation number of carbon in a carbonate ion. So we're going to again apply exactly the same rules. Now carbon could have any number of oxidation numbers depending on what it's bonded in. So we need to take that into account when calculating this. Now oxygen has always got an oxidation number of -2, but that's going to be multiplied by 3 in this instance. We also know that because of the overall charge of -2 of the carbonate ion, that our oxidation number of this entire compound needs to add up to -2 as per our rules. So that means if we've got the -6 contributed from oxygen and the total needs to be -2, it means that a total of +4 must have been contributed from carbon, which means the oxidation number of carbon in the carbonate ion must be +4. You might want to have a look at your textbook on page 77. That's got a comparison of the oxidation numbers of nitrogen in nitrate versus nitrite. Also a nice example. Now it's time for some practice. On page 78 in your textbook, you'll find exercise 3.7. You should try number 1. We've actually done number 1.3 already, so you could just give the other 4 a try.